Good afternoon. My name is Mohamad. Today I'll be delivering on the topic a current excitation based circuit for resistive sensors with lead resistance compensation. These are the outlines we'll be covering today. First, we'll be seeing why resistive sensors and why they have such a wide range of application. Then we will see what are the factors that are stopping their furtherance into more applications. Then we'll see the current state of the art and small modification that we have done to the traditional Wheatstone bridge to get a better performance. Uh, then we'll see the proposed measurement system, how we can implement it, and what are the experimental results that we have obtained. Okay. Resistive sensors have many applications like human monitoring, vital sign monitoring, drug efficacy. Besides this, they are also used in industrial environments for temperature measuring and all these things. Uh, there are certain factors which are responsible for such wide scope of applications, ranging from high sensitivity, robust nature, and these are easily integrable into electronic interfaces. Besides this, one of the most important factors is they have a higher response time as compared to the other counterparts. But however, there are certain factors like the presence of a large baseline, which is very large as compared to the incremental sensor resistance, because of which the overall system resolution is reduced. And for remote bridges, the presence of lead wire is again a detrimental factor. Also, there is a parasitic capacitance always involved with the resistive sensors. And to make the matters worse, this parasitic capacitance is always changing with the measurement as well as the other environmental factors. So these factors are inherent to a resistive sensor and need to be taken care at the system level. Now, conventionally, 3-wire and 4-wire bridges have been used to elevate the effect of lead wire resistances. But however, the other two, they're not taken care of in these resistances. Besides this, they have very high thermoelectric wastages. And this is the current state of the art that we have found from the literature. Now, what we have done in a traditional Wheatstone bridge, we use 4 resistances and an excitation. But because of this, what happens? The thermoelectric wastage is very high. Besides this, the circuit is also highly non-linear, especially when the incremental sensor resistance is very much comparable to the baseline resistance. So the range of measurement for which the R to B converter can be used gets reduced. So basically meaning the range for which the measurement remains reliable is reduced. So to overcome these factors, what we have done, we have used two constant current sources instead of the 2 resistors. Because of this, what happens? The current generation is controlled by a simple resistor, an adjustment register, a resistor, sorry, in the constant current source. So what happens? You get a better power supply rejection ratio. And since there are only 2 passive components involved, the PSRR increases, you get a better sensitivity, the linearity increases, and at the same time, this all happens at the same power consumption. So without increasing any power budget, you get better performances for the same circuit. And then it is followed by the conventional gain amplifier. So this is the measurement circuit that we are proposing. Now, most of the current sources that are available in the market, they are DC constant current sources. But using a bridge network, what we have done, we have changed the nature of the current source from DC to AC. Why we have done? Because if we were using DC current sources, then again we'll be increasing the thermoelectric of wastage, because then we'll be pumping a direct current into the resistor. And in that case, again, the power consumption would increase. So what we have done, we have used an on-chip microcontroller, given a clock frequency, and excited the resistive sensor using a square wave voltage. And the direction of the current is shown by the arrows. You can see the INA performs the differential operation. You get an output voltage. Now, due to the differential operation, the lead wire is compensated for. Next, since we have modulated our information to a certain frequency using the clock, now we want to demodulate it back to DC. So for that, what do? We use a common mode voltage and the same clock frequency. Okay. By using common mode voltage, what certain people do, they use an inverted version of VINA to increase the sensitivity. But then in that case, the offset of the inverted version comes into picture and it degrades the overall performance. So we only have used, we have sacrificed on sensitivity of the circuit, but this measurement system becomes offset insensitive. So we have used common mode voltage there. Now, the voltage VSW is a quantification of our sense. But however, what happens, our sense includes the baseline resistance and the incremental resistance as well. Now, at first, what do we do to calibrate the system? We take this value when no measurand is present. So the value of VSW corresponds only to the baseline of the measurement of the sensor. And using a DC servo loop in the feedback path, we give it back to the reference pin of the INA. And using this, the output of VINA is free of the baseline resistance of the sensor and the offset as well. And since we are using phase sensitive detection at the switch, the circuit is also offset insensitive to the operational amplifier OA1. Now, these are the waveforms that we have acquired at different nodes and points of the circuit. As you can see, VB, which is the voltage at the non-inverting terminal of the instrumentation amplifier, it has been shifted by 2.5 because we are implementing the circuit using a single supply because it is meant for remote operations. So it is to be operated in standalone basis. So dual power supplies cannot be used. Then you see the output of VINA. Again, it has been shifted due to the voltage at V reference pin. VSWC, it is continuously at 2.5, showing the nulling of the output of VSW due to the reference pin. Now, when any measurand is present, the output of VSW will change from 2.5, only giving the incremental sensor value and not the baseline sensor value included in it. And VI shows the corresponding voltage which compensates for these two effects. The first experiment that we did on our prototype, what we did, we kept all the three lead wire resistances of same value and started changing the sensor value with discrete components without any gain in the instrumentation amplifier. So basically we were aiming for a wider range, but we compromised on resolution and sensitivity over there. So we got a range of 13.6 kilo ohm to 54 kilo ohm. The blue dots show the points that we have acquired using an LCR meter by NF. And I don't know if it is visible on the screen. You can see R since calculated at the top using ivory or light green color. So that shows what we have calculated with a worst case error of 2.3%. In the next experiment, what we did, we changed the lead wire resistances by an equal amount from the range of 10 ohm to 25 kilo ohm, and the worst case error was recorded to be 1.6 ohm. These experiments were done for wide range resistance measurement. But in our next experiment, what we did, we brought down the resistance value to 200 ohms. But at that time, we increased the gain by 5 by connected a resistor between the pins, gain pins of the INA. In that case, we got a measurement range of 200 ohms to 1.2 kilo ohms. But the lead wire resistance was only compensated for 10 ohms to 120 ohms in that case. And for that case, what we did the resolution analysis because in low resistance measurement, resolution really matters. So what we did get was a ppm range resolution as can be seen from figure 7. So to conclude, we developed a resistance measurement system which is offset insensitive, is insensitive to the lead wire resistance and baseline compensated as well. Thank you.